everybody, this is dexxcore 1 memory functions. Today I'll be showing off all the memory functions. For this example, I went ahead and just directly included the memory functions, but I've also included the string functions to give an example. But before I start, I'm going to try to explain the difference between a local variable in memory on the heap and pointers. But first example is if you have int b equals 5 and then int a equals b. Oh. Give me a second. Okay. But as you can see, this runs, but the moment you put this variable in parentheses, it is out of scope. Remember to declare it in scope. So it's out of scope. But the main point here is when you create memory addresses locally, the moment they leave their scope, they don't exist. So if we had a pointer, and we were to, well, the thing about pointers is pointers hold memory addresses of either variables or memory blocks, and the moment we put the memory address of b in the pointer, which whenever you want to get the memory address of a variable, you have to use the and sign. And then if we were to now, when you use a normal pointer, it gives you the memory address, and then when you dereference it, it gives you the value. And you can see that the pointer still says 5, even though we left the scope and this doesn't exist. But the thing is memory is like a state machine. You know, if you set it and nothing else changes it, it stays the same. So in this particular case, this pointer that it's pointing to, the variable, the memory itself equals 5, but the variable itself does not exist. So in a way, this is kind of a lie. But basically, how we would create a memory address to a pointer that would stay permanent even outside of scope is where these memory functions come in. For instance, memory new mem new allows you to choose a size, and since we're going to make this a int, we're just going to put size of int. And whenever a memory function creates a memory, well, most of the time when a memory function creates a memory block, it's untyped, which means it's void. So whenever you are taking this memory block and assigning it to a typed pointer, you have to typecast it to whatever type you want it to be. In this particular case, we want it to be a int pointer. And the thing about these memory functions and memory on the heap is scope doesn't matter. This memory will exist until you either free it or your program ends. And like, for instance, you can go entirely without freeing any of your heaped memory, and when the program ends, everything will be cleaned up. But the main reason you want to clean your memory is because if your program was to run for, 10 hours, you would like it to not crash. But then there is memory free, which it's pretty simple. You just take the memory address and you put it in here. And of course, whenever you create a block of memory, it returns an address, and you put that address in the pointer because the pointer holds addresses. And there's really no need for this. But also, out here the pointer is global. And like, another thing too is this pointer variable is not, it's a local variable, so it follows the scope rules. For instance, if we were to put our pointer in here, it would become out of scope, and once we got down to this line, in this particular case, it would know what P was because it would access the global variable. But without this here, you would not be able to access this P because it would say P out of scope, similar to earlier. Oh, I've got this backwards. Okay, now that we've got that. But the point is P's out of scope. And we could put P here, and this would be, in a way, more global, because it would exist for the entirety of main. But another thing is you could put P out here. And the reason why someone would want to put a variable out here and make it fully global is if you had another function that means that both main and Apple could access P. And the thing is too, like, if you have a function that declares a variable similar to a global variable, your function, like, this works, and your function will, if it sees a P, it will automatically choose its version of P over the global version of P. And I do know that if, like, you were in your program and you wanted to access the version of P that was global, you would put some kind of symbol or something in front of P telling C++ you wanted to access the global, but I don't really know what that is. The ideal is there are plenty of letters and names. You probably should just make them unique, but we really don't need our P to be global for these examples. And basically, similar to how you can make an array of 5 and also access the array through these brackets, for instance, the first element, the second element, and the third element, you can create a memory block and treat it like an array. And how you would do this is, right now this memory is holding a size of 1 amp. So you can take that and times it by 5, and now your memory block is big enough to hold 5 ints. And because we've cast it to an int, and this pointer is an int, that means that when we use P, it's treating this generic memory like integers. For instance, this memory is just random binary, and because ints are 4 bytes, and this is an int pointer, it's going to divide the memory into clusters of 4. And if this was a char, it would access the memories as clusters of singles. But basically, the point here is memory block is just a block of random bytes, and it's whatever size you want it. And the moment we cast it to a type, we're telling the pointer, which is of type, to treat this memory as if it is a type. And also, like, I'm pretty sure I showed this, I can't remember, but here we access the value in P, which is 0, but if you remove the star and you use just P, it'll give you the address. 0x is a hex number, and then it has a large number. But basically, pointers just store addresses, and those addresses are to memory. And for instance, if we wanted to take our int value and assign it, we use the pointer, because the pointer, the dereference, there it is, I could not remember. Okay, so when you dereference a pointer, you're getting its value, and that value could either be read or assigned. And this would work even if we had just one int, because the ideal here is the pointer has no idea how big this block is, and this is just a generic block, and we're just accessing it through this P. But one thing too is if we make it big enough to store more, this P dereference here, when we equal to 5, is equivalent to this, as in if you set a dereferenced pointer to a value when it's a array or of values, it always accesses the first value. For instance, P1 is not set. It's random data, which kind of like gives the difference between memnew and memnewClear and memnewClearSet, is that when memnew creates a memory block, it does not clear or modify any of the memory. The memory is just what it is, which is why we're getting garbage data. And sometimes you don't want that. For instance, you might even want to clear this memory to zeros, because right now the memories are not nice zeros like I've displayed with memnew. They're whatever they were before we even claimed the memory. Hell, even a whole nother program could have changed something, you know? But now, when you're switching between different memory functions, definitely make sure of the arguments, because not every function is the same. For instance, the memnew function had just a size, to where the memnewClear function has a num and a size. And the reason this is like this is because when memnew made its memory block, it didn't touch the memory or care about the memory. That was the pointer's job. So we didn't need to know any information. But now that memclear is clearing the memory to 0, it needs to know the number of elements in our array and the size of each element so that it can go through of these blocks and clear it. And I guess now that I'm thinking about it, that probably doesn't have to be. It could just generically go through and clear all the zeros, which I may or may not do that in the future to make mem_new similar to mem_new clear. But in the end, it doesn't matter because mem_new clear set has to follow this protocol anyways. But kind of off topic, but the point is now that we've used mem clear, this data will no longer be random. It's going to be all zeros. And to get that example across, we're going to create a for loop that will loop through all of the 5 addresses. We will run this. And as you can see, besides the first one we set to 5, all of them are 0. And just to show that mem_new does not clear anything. And truthfully, they probably will be 0 because we've done cleared them, but I don't know, I'm hoping we get a different memory address because yeah, because basically mem_new does not touch the memory. It doesn't do anything to the memory. The memory is whatever it is. And because we just recently cleared it to 0, I was afraid that the memory was still going to be cleared to 0. But it seems like these memory blocks are being made in different positions every time. As you can see, this memory is just random garbage. But sometimes instead of setting the memory to just all zeros, we might actually want to set it to a specific value. And that's where mem_new clear set comes in. And because we're actually manually setting the value, the function needs to know what type it is. So we're going to give it a type, and then it wants its number. And since this function knows that we're using ints, we don't really need to give it its size because it knows. So instead we're going to give it a value. And I'm going to give it 76. Another thing too is because we're telling it it's int, the memory in this particular moment knows what type it is. So we don't need to type reference it. You can if you want, but there's no point. And then now the memory down here is all cleared to 76. And the first one we had is 5. There's also the resizing functions, and similar to mem_new, the resizing functions have their clear and clear set version. And basically just like, and the thing with resize, and honestly this has to be with every memory function, I kind of forgot to point it out, but when you use a memory function, whether it be new clear, or new clear set, oh wait, never mind, it's a given. Basically I was going to say you need to put the address into the pointer, but that's a given. But the resize, like when you resize, you would think, okay, I've already got my memory address, so I don't need to return it. For instance, mem resize. That's weird. Anyways, so like when you resize your memory, you have to include the memory address, and then you give it a size. For instance, here we gave it a size of 5. So here we're going to give it a size of 8. And we can't just put 8 because realistically this is 5 times the int size. So for us to be correct, we have to size of int. Because similarly, this memory resize has no idea what this memory is. Hell, it actually just treats the pointer as a void non-type. And what resize does is it'll take this memory address and it will either take this original memory block and expand it, but if it can't expand the memory block, it'll have to create a new one. To give an example is let's say this is random data, and let's just say somewhere in memory this is our block, and let's say that there's another random memory block we've expanded here. Now if we wanted to take this memory block and expand it twice, we can't, because we could expand it once, but the moment we tried to expand it twice, we would run into this other memory block. So there's a chance that, like for instance, if we wanted to expand this memory block by 1, it can. So it's done. You know, it kept the same memory address and just expanded it. But if we wanted to upgrade it 2, we can't do that without truncating the other memory block. So what it does is it will create a new memory block with the added 2, and then let's just say this is random data. I know binary can't be 3s and 5s, but I'm just trying to make the memory unique. But let's just say that's in there. What it will do is it'll take that and copy it into the new memory block, and then it will take this memory block and just remove it, which essentially just throws it back in the wild for any other memory function to grab, and now it sends a new address. And the reason why this is important is because knowing that this mem might need to give you a whole new address when resizing, it's very important that we return whatever mem resize gives us. Even if it gives us the same address, we still want to return it because there's a chance that it's going to give us a different address. But also, when memory resize increases its value, it copies the original values and then it adds whatever new data is there. Mem resize does not modify the new values at all. It's garbage data. But mem resize clear, this will set all new data to 0. So to give an example, we're going to display 8. Oh, yeah, okay, so we got to cast point this because it's basically a generic void memory block, and since we increased it, yeah, either way you still got to do that. And to make things clearer, we need a divider, because I don't even know what I'm looking at here, just a bunch of numbers. Now in this particular case, it kind of slurps because we've upgraded the new memory 3 places, and it shows 3 zeros. This memory is not zeroed out. Those memories just happen to be 0. Let me see if I can get it far enough into new memory that it is random data. Okay, well, oh, okay. Basically, memory's random. You don't know what the hell it's going to be. I could have just probably re-ran it and it would have been random. Like, for instance, like this memory's always changing. Like, right now it's 0. Now it's this random garbage. And then when I run again, it's 0 again. So, like, the point is you know, you look at that and you're like, ah, okay, that's clear in my memory, that's cool. But it's not. So then when you do run your program and you've seen this and you try to rely on it, you're going to realize that there's going to be a huge bug, because as you can see now that I've ran it, the memory's trash again. But that's where memory clear comes in. And memory clear has no resize clear. I was like, what in the heck? Okay, anyways, memory size clear takes the memory, the old size, and the new size. Now, we know our old size is 5 and our new size is I guess the reason why this resize clear function requires the old size and the new size is because it will actually go in and clear the data. As you can see, it's 0, and it needs to know where to start clearing zeros and where not to, because we know that when we increase a memory size, all the old data is copied into it and then it clears. And even if the old data isn't copied into it, it's the same memory address, it still needs to know where to start clearing. For instance, it's 0, I can make run and it's still 0, make run, still 0. It's always going to be 0 because it's being cleared. Then there's memory clear set. This is basically like our mem new clear set, where we can set a specific value. For instance, we set 76. And of course, whenever you use functions, definitely look at their syntax, because this one's different. Memory, old memory, new memory, then value. I guess it wasn't that different, but still. And, you know, if we wanted to just continue the line, because as you can see, we cleared to 76, and then for some reason it just does 0. You know, we'd like to continue that, because our code says, hey, if value 76, then who gives a crap? I don't know. The point is that value might, for our program, indicate a clear slot or something. You don't know. So it's just best to keep it. But now, as you can see, all of our memory is cleared to 76, and of course we can run it multiple times. I probably should stop doing that, but it's just there. And then, besides our resize functions, we have our memcopy and memset. Basically, memcopy, you have these generic memory blocks, or should I just say pointers? You have pointers with memory addresses, and what you do is you give one pointer, and then the second pointer, and then you give a number of bytes you'd like to copy. Okay, I thought this was compare. Okay, but basically what it does is it just takes the source and copies it to P. And the thing is if this destination had data previously in it, you are going to override that data with num bytes in source, starting at the beginning. Now, one interesting thing to know, and it's kind of pointless here, so I don't know why I'm showing you this, but let's say we had mem copy, and I had my original P list that's up there, and then I had a mem, which is just another generic memory address, and we would like to take the mem address and put it into P, and we'd like to take, I don't know, let's just say 2 ints. Well, the thing is right now, the way this is laid out, memory copy, it's going to take the beginning 2 ints, and it's really not even taking ints. Really, it's just taking generic bytes. But we put a 2 in it, and we gave it the size of int, and clearly our pointer p is being treated as an int. So this is int data. Now we could take model data and shove it in p, and because p is an int, it's going to be random ints. It's just, it depends however you're viewing the data. And, you know, it puts it at the beginning, but what if we actually wanted to, down here in our memory block, we wanted to put it like in, start putting it into the third row down? Well, what we could actually do is we can take our pointer and +3. And what this is saying is I'm a pointer address to a memory, to the beginning of your memory block. And I also know I'm an int. So when you add 3 to me, assuming int is size 4, I will add 3 times 4 to my memory address. And then that will put you in possibly this area. Maybe this area, I don't know exactly, but the point is it'll put you somewhere in your memory block. And the best part is when this function's done, your p still references the beginning of your memory block. You just temporarily went into the memory to the third element and added 2 ints from the beginning of mem, because what it does is it'll copy this memory into there. Now that's probably an over explanation, and I probably should have shown the code, but I'm trying to want to show something else, and time is dragging on like always with these videos. And memset, it's kind of pointless, but as you can see here, basically it just sets a byte, and that just means a char, because a char is a byte. So you pretty much just go in, you take your string array, you put in the memory address here, you put in the byte you want to change, which we're putting a char, and then the number in, like 1, 2, 3, 4, 5, 6. It'll change the 6th one. And then you have your memory compare function. And what it does is it basically, you put in your mem1 and mem2 and number of bytes you want to compare. And then this is your offset start. So it's kind of like what I was showing you earlier when you take a pointer and you add to it. That's kind of what this does. It's optional. And then you can compare how many bytes you want to compare with whatever area you're going to start at. And these are all considered void pointers. So that means your start will be increments of 1, not 4 like with our int. But anyways, what I was wanting to show you guys, which is pretty cool, is, and the main reason I included the string here, is we're going to create an object, which is a structure, and we're going to call it cat. And we're going to give it a string name, and then we're going to give it a constructor. Now, what a constructor is it's basically saying when I create this object, run the constructor. And we can make the constructor where it can take a name. And then in the constructor we can set the actual name for the object or the struct to the name that the user gave us to make the cat unique. And then std cout meow. And the reason why we're putting this here is so that we know the object was created. And you can also have deconstructors, which are called when the object is destroyed, which is also really cool. And we're going to do the similar thing. We're going to say deleted name. That way we also know what was deleted. And I'm going to remove all this actually, just give you a clean start, and we're going to std cout end. Actually, let's just end. And this is basically just going to show us the end of our program. And we're going to create a cat. Yes, cat kitty equals cat. We're going to name it shadow. And hopefully this runs. Okay. So as you can see, we've created a cat object called kitty, and we named it shadow. And when it was created, it meowed. And then we have the end here. So this was called, and then when it reached out of scope here, it deleted shadow, our cat. But the whole thing is out of scope, you know. You put this down, and then you do it. It sees that shadow was deleted before end because it left scope. But this is the whole local variable and whatever. But basically, C++ has these keywords new and delete. And seeing how this is becoming a memory in the heap, this can no longer be a cat. It has to be a cat pointer. And basically, the ideal here is the cat was created, but even though it left scope and the program in, the cat was never deleted, because whenever you use new and delete in C++, it works like our memory functions. That memory will exist until you explicitly delete it. Oh. Now, as you can see, shadow was deleted. But the main point is if you're going to create something with the new keyword, you definitely should delete it with the delete key. But what we're going to do here is we're going to make use of these memory functions and create a list of cats. And this is where the mem clear set function comes in, because cat list is going to be a cat pointer equals mem new clear set. And this is going to be a cat pointer, and we'll make 5 cats. And we'll give it a value null pointer. Now, this is going to get a little weird, but this is also a really good lesson to teach you, is we have an int pointer, and we know that equals a list of ints. But what if we wanted a list of int pointers? Because in the end, when we create a new cat, we can't put it in a cat. We have to put it in a cat pointer to hold the new cat's address. So when we create this list, we're not going to have a list of cats. Like, you know, a cat pointer holds a list of cats. We want to hold a list of cat pointers. And how this works is you create a cat pointer pointer, which a cat pointer pointer is a list of cat pointers. I know that's crazy, but honestly, it's actually pretty clear. Like, especially when it's explained. But the point is now we have a cat list of cat pointers, and we have 5 of them, and we set them to null pointer. And the reason why we do that is because when we have a cat list of objects, we want to know, does cat element 0 have a cat? Does cat list 1 have a cat? And we can check that by saying if cat list equals null pointer, there's no cat. But anyways, basically what we're going to do is we're going to take this cat list and we are going to set the 0 element, and we're going to create shadow, and then we're going to delete the cat. But the thing is we can't delete the cat like this, you know. And you know, we could easily say, you know, delete cat list element 0, but we don't want to do that. And that's the whole point of what I was explaining earlier. No, what we would do is we would make this automatic. We would say for loop int I 0 I less than, there's 5 elements in our list, and then I plus plus. And what we would say is if cat list I doesn't equal null pointer, that means our list has a cat in it and we want to free that cat. So we're going to delete cat list I. And just for safety, I mean, it's not required because we're at the end of the program, but you know, if this is a function you want to call over and over, you should probably make it usable. But we would set null pointer to the element that's been deleted. And now we've created a cat and it deletes shadow. And the best thing is I can come in here and I can create another cat. Let's just put it in 3, just to show that it's going to work no matter what. And you know, we'll name this cat Buddy. And now, in the end, it deleted shadow and Buddy. And if we really wanted to, we could even create a function like void, because it doesn't return anything, free cat list, and then just copy and paste this in here. And now every time we want to end the program, we just call free cats. Honestly, I would just call it free cats because less the type, but basically just call that function at the end there. Now this wouldn't really work as is, and the reasoning being is you'd have to give it a pointer. And how you would do that is you would just create a function here with cat pointer, call it cat list, and then in here you would put in cat list, and then it would be fed to the function. But that's not really the point. The point is mem clear set allows us to set our entire list to null pointer, and this is great because that's what we want. You know, I don't want to manually do that. And what's even great is with the mem resize clear set, if we wanted to increase the size of this list, now we can literally, now old size, that would be 5 times size of cat. Actually cat pointer, because this is a list of cat pointers. And then the new size, let's just say we want 8 of them. And then the value, we know that we want them to be null pointer because there's no cats there. But let's see. Actually, I'm going to steal this. And even though we resize the list to 8, because that's what this function does, we know this function works. Actually, I can do that. I can just put this to 8 real quick. Because what if it doesn't work? But anyways, what we're going to do is we're going to say if cat doesn't equal null pointer. Oh, and another thing you can do is structs can have functions. For instance, in here, we could create a function that returns nothing that's called eat. And in here, we can return name is eating. I know, it's a little odd, but it's just to give the point across that we can call functions from these bad boys. Make sure everything's right. Okay. But anyways, in our list here, if cat list doesn't equal null pointer, that means there's a cat in there. So, now, normally if you're dealing with a cat, you would put cat dot eat. But because this is a pointer, we have to reference the function with an arrow. But I always say, you know, a pointer needs a pointer because that's an arrow pointer. But also, else std, make sure there's a new line in there. Yep. Okay, std cout none. What this will essentially do for us is now trying to see what's wrong here. Well, first off, I need a space here, but that's irrelevant. Well, Oh, okay. So here's what happened. Obviously, what I was telling you earlier is this may create a new memory block. And I don't think that's the case, or else these wouldn't have worked. But even still, just for completeness, we should probably add that in there. And we'll see. Maybe that'll fix it. Yeah, okay. That's weird. Oh, because memory is untouched. Okay, the whole thing is, you know, if you set memory and then you delete your reference to that memory's not going to change. But the point is this memory function, we failed to put it into our original memory. So, you know, when it came back out, we were using the old memory, which only had 5 slots in it. And it really had 8, so that was my bad. But it's a good example. Don't ever forget to return your memory into your thing. But anyways, the cool part about this is we can literally create objects in our list on the fly. And not only that, but we can call their functions. And we know, like, you know, if I wanted to create, like, okay, Shadow is eating, none, because I skipped one just to show that this is great. And then Buddy's eating, and I could even create another cat, but this could go even further, like, because when we're creating these cats, we don't know which one to put in, so you could literally create a function for creating cats. For instance, you can use a for loop to loop through this list, and then you say if it equals null pointer, then create a new cat. And that way, all you have to do is call a function called new, or yeah, new cat, give it a name, and have it where it shoots you the index of where that cat is. For instance, cat index equals that. And now when I call new cat and I can name it, I'm going to get an index where my cat is. And now I can call cat list with my cat index and call my function eat. And, you know, if I want to free my cat, which if you're going to create a new cat function, you might as well call a free cat function. But the point is this free cat function, you would put your cat index in it, and then the function body would use that index to go into the list and delete the cat and set it to no pointer. Now I know that was a lot thrown out, but the video is getting kind of long, so I don't really have time to demonstrate that. But basically, you know, and my memory functions right here, these are just generic C memory functions. So you may not have these, but you have C functions. So you can do all of this awesome stuff on your own. And I highly suggest you try it, because it's cool. And it gives you so much power, because essentially these objects we created, these cats, these are game objects. This is how I create game objects. I mean, there's some automatic scripting involved, but I mean, if you're just creating your game in raw C++ and you don't really care for automation, I mean, here you go, you know, give that cat some int HP. I mean, if you're into that, you might just give it a hunger meter, like a hunger level, and let's just say hunger is 10 and int hunger max is 10. And maybe over time your hunger will decrease and you gotta feed your cat or something. But anyways, this has been Memory Functions, and I hope you've learned something and this has been helpful. And next time I'll more than likely be covering string functions, even though I kind of covered them in here.